Okay, so today we are starting power spectral density discussions. Power spectral density. So let's remember what we have studied in the earlier, let's say, a few hours. If I have a random process, which is Weisstein stationary, and if this random process is processed, stochastic process, let's say, is worked on by an LTI system, then the output y of t, we have seen that this is also Weisstein stationary, and it has this kind of an autocorrelation function. We have solved some examples on this. Maybe you can remember, we have called this part deterministic autocorrelation, etc. Now, let's say that I would like to calculate convolutions. What comes up in your mind? How can I easily compute convolutions? Now, you can say that this is one of the major things in 301, signal processing course number 1. We evaluate these convolutions in the Fourier domain, isn't it, or Laplace domain, for the sake of computation, let's say ease or feasibility. So one idea is to evaluate output autocorrelation. We can use Fourier transforms to avoid doing convolution operations. Indeed, power spectral density is, let me write it over here, related to this idea, but it is much more important than computational, let's say, ease. Okay. So what do I mean by this? Now let's define power spectral density. Power spectral density. So let's say that x of t, Weisstein stationary, and then we have our x of tau, autocorrelation function. Okay. Then we define the power spectral density like this, S x of f. So this is the power spectral density. And what I would like to say is, this is simply the Fourier transform. Okay. This is, let me write it like this, Fourier transform of autocorrelation function. I think it is clear, Rx of tau. Now you can say that this is not looking like a Fourier transform because in the earlier courses you were studying Fourier transform when this part was called omega. Okay. It was a little bit different. So in this course we are using this definition of Fourier transform. This definition means now the frequency variable is in hertz, meaning that oscillations per second, 50 hertz, 60 hertz, etc. Okay, so this is radial frequency, but f. So my frequency variable is right now in hertz. Actually, this is a much more easier definition. Why is an easier definition? Because the inverse Fourier transform becomes almost like the forward Fourier transform. Only difference is this plus minus change in the exponent. If I use omega over here, maybe you can remember there is 1 over 2 pi factor in the inverse Fourier transform. Okay, that was causing some difficulties in the sense that in the duality application and so on, there are 2 pi factors coming up, isn't it? There are things like that. But this one is symmetric definition. It's very convenient, and this is the definition that we use because it's a practical course. In this practical course, we will be thinking about frequencies in hertz. Okay. Of course, all Fourier transforms are the same. Whatever you call, it is the same Fourier transform. So let me write this part again then. Okay, 2 pi f tau. So this is the autocorrelation function, and I take its Fourier transform, call it power spectral density. So with this definition, let me give this a number or a sign. Star in Fourier domain becomes, so how can I express this? Fourier transform of Ry of tau is equal to Fourier transform of, I have this thing, Rx of tau convolution with h of tau minus tau. Okay. But let me go this way. So this is power spectral density, Fourier transform of autocorrelation function, convolution theorem in action. So Fourier transform of this is, by our definition, h of f. How about the Fourier transform of this one? You can look it up, or just believe me that it is this. It's very easy to prove also. Okay. H conjugate f. So at the end, this relation becomes okay. It becomes something like this. Indeed, it's easy to calculate, isn't it? Instead of doing convolutions, you are calculating the magnitude response of the filter. This is called the magnitude response without the square. If you take the square of this and multiply by the power spectral density of the input, you get the output power spectral density. How convenient. Okay. So this is indeed easy to calculate. So to better understand, why we call, let me say, Fourier transform of Rx of tau as a power spectral density, we need to go over its basic properties. So what do I mean by this? Now I can take Fourier transform of anything. So somebody is calculating the Fourier transform of this thing. But that person is calling this power spectral density. So what is special about this? Well, I can understand why this is called spectral. Because this is in the spectrum, okay? In the Fourier spectrum. So, but how about why do we call this power and why do we call this density? Okay, if we think about it. So let's see. Now, but maybe because before starting that, let's emphasize this one more time. Rx of tau, Fourier transform relation, Sx of f, and then let me write this one more time. Sx of f is equal to Rx of tau d tau, and from the inverse Fourier transform, j2 pi f tau df. So this is the forward Fourier transform as we have discussed. Now in the Fourier domain, if I apply inverse Fourier transform, I get the relation back. Okay, that is it. So this is our definition. Okay, let's go ahead. So let's look at the properties. Number one. So what was the title of this? Area under PSD function. So sometimes we use PSD for power spectral density, but this is somewhat confusing because we also use PSD for positive semi-definite. Unfortunately, it's like that, but one of them is for matrices, let's say, but this one is for function, I think it will be clear area under power spectral density function. So what do I mean by this? Now this is Rx of 0 minus infinity to infinity df. So this is the area, total area, let me say it like this. Total area under Sx of f. So can you see why this is true? This is equal to Rx of 0. How about this? Inverse Fourier transform relation. So this is an equality. So insert 0 over here for tau. Okay. So the way I remember this equality is, if you are looking for the value of the function in one domain at 0, that value, left-hand side, is equal to the area of the function in the Fourier domain, in the other domain, total area of that function in the other domain. Okay. If you don't, there is no 1 over 2 pi factors over here, as you see. So put 0 over here. The value in domain number 1 is equal to the area in domain number 2. Okay, they are Fourier pairs. Similarly, the 0 in the other domain, the value at 0, is equal to the area in this domain this time. So this definition is symmetric because of that. It doesn't matter whether you are thinking this is as time, this is as frequency, because they are the same right now. Okay. So in one domain, we have this, and the other domain, we have that. But how about this Rx0? So Rx0, as definition, expected value of, am I right? X square. Or if this is complex valued, let me write it like that, magnitude squared. Okay? So how do we interpret this? Previously we have talked about this. We were calling this total average power. Well, not the total, but let me say the average power, because average power of process x of t. So again, this is an averaging operation. Why do I call this power? Because as an electrical engineer, well, averaging over here, this is power because if you think about it like a voltage waveform, square of the voltages, if you apply it on a resistor, V square over R. Okay? That is related with the power quantities. So all energy quantities, power quantities, they are somehow related with this second power operation. Okay? So this is our average power of the process x of t. And if this process is deterministic, and let's say that this is the time average, this becomes the average power consumed by a resistor, etc., by a machine, etc. It's something like that. But this time, this is an average taking place over the ensemble. So this is the ensemble average. It's not a time average, obviously. Okay? So this is over this random process, sample number 1 at t. Okay? Something like that. I'm talking about that. So I get a number for this, and I'm calling this the power of this process. So I think it's clear right now. We see that, so the total area under Sx of f is the power of this process. Power of the process. Of course, this is limited to Weissan stationary processes. If that power value is changing all the time, I mean, there is not much to do. So all of these definitions, there is only one variable, Weissan stationary processes, etc. Okay. Now, this explains a little bit why we call this power, I guess. Power spectral density. But we should say more. Now, why is this a density? Let's see. So number 2, second property, is x of f is real valued. Okay. So let's prove this so that we can get closer to why we call this a density. Okay. So we will use the Hermitian symmetry property of Rx of autocorrelation function. So what was that? Let's remember. Rx of tau is equal to Rx of minus tau conjugate. Okay, that was this one. Now how can I use this? Let me write the definition for power spectral density. So I'm trying to show that it is real valued. It is this. Fourier transform of this. Okay. So how can I do? What can I do about this? So if I take the conjugate of this, let's say. If I take the conjugate of this. Okay. So how about moving the conjugate inside? That kind of an operation. Okay. Do you agree? Conjugate is moved. Well, I can sum them first and then take the conjugate. I can conjugate them first and then sum. That is the idea. They should be the same. Okay. Very simple. But this doesn't look like it. So what do I want? I want this conjugate to be exactly equal to this, such that I can say that this is real valued because it will be equal to its conjugate. But this doesn't look like Fourier transform, isn't it? So I will do again a variable change. Tau prime is equal to minus tau. And I will use this eventually. Minus infinity to infinity. This is tau prime, d tau prime. Again, instead of tau, I'm writing minus tau prime. So this should be minus d tau prime. But again, changing these limits, I get that. So from the symmetry property, this is equal to Rx of tau. Okay. Hermitian symmetry property. So, and finally, we get that result, Sx of f. So this is the end. Because this is nothing but power spectral density definition. Fourier transform of autocorrelation, as we did over here. So it's a little bit interesting. Now, the area under this function is equal to the process power. Furthermore, this function is always real valued. There are no complex numbers involved. But I need more. So one more thing. There is a third property. So third property is, so I have said that this is real valued. It's not complex valued. Furthermore, it's non-negative, i.e. Sx of f is non-negative. Non-negative valued. So how can I check this one? Well, this is a proof, but it is not a very, let's say, there are some details being missed out, but that's okay. So let's assume that this at a special frequency fx, let's say, is negative. And hopefully we will have a contradiction at the end, and then we will say that this cannot be negative, okay, at the very end. So let's assume that this power spectral density at a frequency value, it's a real number, is negative. Okay. So I will do x of t. Now I will construct a filter. Now this filter is a bandpass filter. Okay, something like this. So this is my filter's magnitude response. Do you remember the magnitude response discussions? Okay. So this is the origin and so on. So what is the bandwidth of the filter? you can say this is the bandwidth of the filter, and so on. Now the output processes y of t. Okay. So what is special? Center frequency is fx. There is a bandwidth, and for this fx value something special happens. Power spectral density is assumed to be negative. Now, what should I do? Now I know that Ry of tau is equal to, one more time, Rx of tau, convolution width. This filter, but let me denote this bandwidth of the filter somewhere over here, because I will change it later on, bandwidth. Now in time, in let's say non-Fourier domain, because this is a tau domain, correlation domain, I have this, bandwidth minus tau. Am I right? Nothing new. Processing of a wide-stand stationary process by an LTI filter. Nothing new. Now, if I take the Fourier transform, and we have studied this, this becomes, is it still there? It is this one. So the magnitude response of this filter is squared and multiplied by this. Do you agree? So this is always correct. If it's wide-stand stationary process, I have a filter like that. Output power spectral density is this. Now, how about this? Let's go over here. Ry0. What was Ry0? The area under this, am I right? So this is minus infinity to infinity. So area under this should be the output power. Okay, am I right? By definition, I have this. But this is, because of this filtering operation, it's always 0 everywhere, except this region. So this is actually, integration is in the frequency range of from here to there. Okay. So how can I write this one? I can write this one as f minus fx smaller than, let's say, bandwidth over 2. Okay. Because this is bandwidth over 2 to the right, this point. This is bandwidth over 2 to the left. Okay, this part. So frequency is, sorry, this is not fw, this is fx. Okay. Frequency is, if you check this, fx plus bandwidth over 2 and fx minus bandwidth over 2. Okay. Then this becomes, if I write this, let me go with this. How about this? You know, the magnitude response of this. So let me call this passband of this filter as, let's say, A. So this becomes A square. Okay, magnitude of that. That is a df. So if I do this calculation, now I will say that this is the inaccurate part. Now I will say that this is equal to do you agree? So how can this be? So what's going on? Actually, take this a square out of this integration. Then you are integrating this function over this interval. So if I, let's say, sketch this function something like this. So I'm integrating, this is my Sx of f, let's say, for the sake of simplicity. I'm integrating this Sx of f from here to there. So this is the area, this area, essentially. So this is approximation of this area as the center point of this function times the, this side of this rectangle. So I'm approximating it by something like this. So you can say that, of course, this is not very accurate, but if I change this bandwidth, if I make this smaller and smaller and smaller, it will be getting more and more accurate. Okay? If I make this bandwidth smaller and smaller and smaller, then this would be more accurate, provided that this function is continuous. Am I right? This is the whole idea of calculus, essentially. Okay. So I am approximating this integral what we call by a Riemann sum, something like that. So let me write that as a comment. So as I have said, this is a free variable. There are no constraints on my bandwidth. I can make my bandwidth maybe 1 hertz, maybe 0.1 hertz, maybe 0.0001 hertz. So it can be smaller and smaller and smaller. Note, so this is the approximation. Note the final approximation becomes more and more accurate as bandwidth gets smaller, assuming this is almost always the case, Sx of f is a continuous function, continuous at f is equal to fx. There are some details like that. Okay. But intuitively we got the feeling, I guess. Okay. So this is, let's say, my final result. Then let's say that Ry0 is approximately equal to this. So this is supposed to be greater than or equal to 0. Because this is, as I have said, expected value of y square or magnitude square of this. It's supposed to be greater than or equal to 0. So a square is positive. This is positive. So how can this be negative? So this is a contradiction. So Sx of f, fx, cannot be negative, negative valued, since, let's say, let me put double star over here in case of confusion. Double star should be satisfied. That is it actually. Actually, this is a proof by contradiction. For example, one of your friends is telling that, you know, the power spectral density at the frequency of 100 Hertz is negative. Then you tell him that, okay, let me construct a filter over here. You put a filter, let's say of bandwidth, let's say 10 Hertz. So I have said center is 100, from 95 to 105. Okay. Then you process this. So this is supposed to be at the output, another process, Y-sense stationary process. And the power of this process is this. But according to this calculation, it is supposed to be approximately equal to this. If I make my bandwidth smaller and smaller and smaller, this is always valid. So how can this be negative? Because at any frequency that my friend selects, I can always construct an imaginary, abstract filter with very small bandwidth. So I can always have only that frequency component passing out. Okay? And that will be the power of that process. Am I right? So that should be positive. If I make tiny and tiny and tiny filters, bandwidth of the filters. So that is it. So we see that is the end actually. This is the end of the proof. So let me write a conclusion. So Sx of f is a real valued, a real, non-negative valued function whose area is equal to the power of the process. Power of the process. So let's think about it. So does this thing look like power density function? So let's try to understand this density. So why do we call this density? So let me give a physics example. Because if I give examples from different, let's say, fields, maybe that's more useful because you have some earlier experience in such calculations. So let's assume that this is like a metal bar. Do you remember Physics 105 questions? Density of this metal bar, things like that. So density of this metal bar is, this is let's say 1 meters. Maybe this density function is, let me sketch it over here like this. So this is 1. Maybe something like this. I'm just making this up. So what does this mean? You know, this metal bar is heavier somehow over here. So this metal bar, let me mark this heavier parts. So it's lighter over here. So it's heavier, lighter over here, maybe a little bit heavier over there. Do you see what I mean? Okay. Or you can think of this, maybe this metal bar, I'm putting some weights on this bar. So maybe more weights is placed over here. 1, 2, 3, 4, 5. 3 weights plus placed over here. 3 weights, 1 weight, and so on. So what is the total weight of this bar? 5 units, 3 units, 3 units, and 1 12. 12 units of weight. If you look at the density of this, now the density is, this is what we call discrete density. Now it's 0 over here, there's an impulse of 1. At this location, there is impulse of 5. I think it's clear. Impulse of 3. At this location, impulse of 3. Okay? Something like that. These are the distribution of these weights. This is what we call the density function. So what is the total mass? So the area under this function, this density function, so this is the, let's say, mass density function, is total area becomes the total mass. Okay? Or summation of this becomes the total mass, 12 units. Okay? So how about this? If I integrate from here to there, so that means that I'm cutting this bar, metal bar, and I'm taking this part out. What is the weight of this part? Well, you integrate this density from this part to this part. Okay? That would be the weight of that segment, that piece. So this is the definition of this density. Okay, density function. So we have a total weight. That total weight is distributed, you know, on this axis according to this. This is a continuum. This is in the discrete case, and so on. So we have the same idea. Now I have this area on this, under this function as process power. Okay. And exactly like this, area under this is process power. Maybe if this is like the spectrum, you would be expecting that in this band, there is much more process power, let's say somehow concentrated in this band. In this band, there is very little for this spectrum, very little process power, etc. That kind of interpretation. So do you see that this realness is important? Because otherwise it's complex valued, you know, how can I say that this is the density? Okay. How about non-negativeness? Non-negativeness is also important because, you know, I don't have negative weights and so on. Okay. So it should be either 0 or positive valued for the density function. So this is the same thing with the probability density functions, probability mass functions. These are the reason that these are called, you know, density functions, etc. Okay, so let's have, you know, an example to see this in action. Now this is first example. X of t is a cosine 2 pi f0 t plus theta. This is our familiar example, what we call random phase cosine. Do you agree? So previously we have studied this, well, in terms of everything. We have calculated autocorrelation, etc., etc. So let's use those results. So what's the question? Sketch, you know, Sx of f, something like that. Well, let's say solution. I won't be calculating, but our x of tau is, just to remember, x of t, xt minus tau, product under expectation. So this is equal to, I'm just writing this from memory actually, 2 pi f0 tau. Okay. This is already in your notes, and we have spent so much time on these discussions. Now that is it. Now how about its power spectral density? This part is the Fourier transform calculation. So how about the Fourier transform of this? a square over 2, this Fourier transform. So how can I calculate the Fourier transform of this one? This would be 1 over 4. Do you agree? At least, since the Fourier transform definition is a little bit different, it's over here. But you know, the main idea is always the same. This cosine is nothing but e to the j 2 pi f naught tau plus minus j divided by 2. Fourier transform of this one becomes this. Fourier transform of this one becomes that. There is 1 over 2. Move this 1 over 2 out of this bracket. This 2 becomes 4. Things like that. By the way, I have placed some notes on the web at the ODTÜ class web page for these details of this Fourier transform, some properties like shift properties, modulation properties with this definition. Okay, so they are in general a lot easier, but just to make sure that you know we are on the same page, that is, we are using the same expressions, I have placed that document on ODTÜ class. Please check that. Very basic, but something like that. Now, let's see. If I sketch this, what do I have? Now, S x of f. I will sketch this one. So this versus frequency. So there's an impulse of weight a square over 4. And at the symmetric location, a square over 4. That is the end. Okay. That is it. But how can I think about this? Now, let's say that this f naught is over here, and I have a filter, bandpass filter, over here. Again, this is my filter's magnitude spectrum. So this is the bandwidth of the filter. This is this. So this is A cosine 2 pi f naught t plus this. So this is random phase cosine. So do you remember how we sketched the realizations of this process? You know, realizations are just cosines of amplitude A, but the starting phase is random. Okay, something like that. Maybe it starts at the peak. Okay, something like this, etc. So only the phase is random, random phase cosine. Now this is the output, y of t. Okay, so you don't know anything about random processes. So does this thing make sense to you? If I apply such a signal to this h of f box, and the filter is something like this, do you think I will have a output, non-zero output, if the filter bandwidth does not include this frequency of this? So f naught is over here, minus f naught is over here. So it shouldn't be, because we see that this filter is suppressing, it's an ideal filter, everything outside of this frequency band. Okay? It's suppressing that. That's the task of bandpass filter. So whatever I select over here, theta, so it should be 0 at the output, isn't it? Because this passband of this filter, this bandwidth, does not include f naught. Okay, that is the idea. So what happens if I include this somehow, if I move this filter over here, and if I include this f naught frequency? Now you can see that, you know, whatever the input, let's say that it's not amplified by 1. So whatever I have at the input, it passes through the output. No changes. Okay. That is the way it is. So do you think this is insightful? Well, not insightful, but do you think this is reasonable, or do you think this power spectral density also matches this kind of an insight? Indeed, it matches that kind of an insight, because what we see is that It says that if I put, let's say, this kind of a filter over here, f1, okay, so I will be integrating the center frequency. So it says that, let me write this, sy of f is equal to sx of f, this thing, times h of f magnitude square. Okay. So over here, this frequency band, whatever I have over here, this bandwidth, will be processed by this filter. But there is nothing over there at the input side. Okay. That is the idea. So what I observe is that this power spectral density is compatible with our, let's say, expectations or intuitive understanding of this. But there is something, again, a mismatch. Because when you think about a realization of this process, you are thinking about a, let's say, this black function, red function, blue function, etc. But this power spectral density, please remember, it is related with the ensemble average. Not a particular realization, but an ensemble average behavior. What do I mean by that? This is the Fourier transform of Rx of tau. And Rx of tau is, it's not a particular realization, obviously. So we are looking at this expectation as ensemble average. Okay, I have this. But still, this is what we want. So for this, let's say, this kind of a, let's say, waveform, random phase cosine. If somebody tells me that the power of this waveform, this kind of a process or waveform, is located at any other point other than f naught in the spectrum, I would be saying that, oh, okay, you are making a mistake. Am I right? So power spectral density tells us that this power distribution of this process, random phase cosine, is located at this point and at this point, and it's nowhere else. Whole power is concentrated at those 2 points. So this is the good news about this power spectral density definition. It exactly matches what we expect, at least in this example. And the utilization of this filtering idea, so let's see, this is actually what is done in many cases in practice. Let's say that you have an antenna. This antenna is intercepting a signal. Then you don't know what this signal is. Then what you do is, you construct a filter and you look at the power in this band. Okay. So let's say that you are running a spy agency. You are trying to listen to someone. Then you try to listen this band. So how do you listen to this band? Well, in this band, maybe there is some noise, maybe there is some random other messages are coming through, etc. But over here, at the end, you have a y of t. Then you try to calculate this expected value of yt magnitude square. So you say that, well, I have filtered this band, and if I do some kind of an averaging, then I get this value. So if this value is equal to 0, like in this case, then you'll be saying that, okay, there is no activity in that band. Okay. There is no activity in that band. This is actually what is being done in frequency analyzers. You change this bandwidth, you do this averaging, let's say, over many cycles and so on in time domain, etc. So this is also, quite a practical setup. But for our purposes, right now, we are more focused on the understanding of the random processes, which is this says that this random process, this type, has power concentrated at this point and nowhere else. That is it. Okay, now let me have one more example. Here is one more. Now x of t, actually this is supposed to be 2 because we have started with 1. X of t, now sum of something like this. Over here, AKs are 0 mean and uncorrelated random variables with variance sigma, let's say, k square. Actually, this was also one of our earlier examples. Maybe you can remember. Now again, solution, problem is the same. Sketch this. So how can I find the autocorrelation of this? Rx of f, Rx of... Sometimes I use small, sometimes I use capital letters. It doesn't matter actually. So this is equal to, we have done this calculation also before. Let's say, so it's in your notes, check the earlier notes. Okay, this is the autocorrelation calculation. Uncorrelatedness is used, zero mean is used because in this calculation I have to do this operation with conjugate. Conjugate is also important. So if I do this multiplication, they are AK times ALs. They are zero mean, uncorrelated means cross products will be equal to zero if you do this multiplication. You have then AK magnitude squares. That would be giving me this term and things like that. It's not a very difficult calculation, it's in your notes. Now, Fourier transform step. This is even easier. F minus Fk. So the frequency is at Fk. If I take the Fourier transform, there is a Dirac delta located at Fk, that frequency. Okay, that special frequency. So if I sketch this over here, Sx of f. Now at f1, let's say f2, I'm sketching them at different heights for visual clarity. This is F capital K. This is its weight. This is the third one's weight. Something like this. So this is the frequency in hertz and so on. So what do we see? Now, let me erase. Okay, let's keep this. Let me use this part then. Because there is not much to write. So let me use only this part. So what is Rx of 0? So let me write total process power. Well, it is equal to this when tau is equal to 0. Okay? So this is equal to summation of all of those weights. Okay? Exactly like this one. Okay? All of those weights. So what do I see? Well, I see that if I put, again, process this, x of t, random process, with an LTI filter, and if that filter passband contains this frequency, do you see what I mean? Now I have this x of t processed by a LTI filter, let's say h of t. At the output, you have y of t. If the magnitude response of this filter is something like this, 1, okay, so red one refers to the magnitude response of this filter, then clearly this term will be passing through, and I'll be observing this much of power at the output. Okay, so it will be, again, filtering concept. It will be selecting the first component in this sum. So we see that now this power, if this filter is bandwidth is very large, then at the output side I have a random process which will be passing through all of these components, meaning that this process passes through without any attenuation or amplification to the output. That will be it. Now we see that why this is called maybe power spectral density a little bit more. Because what we see is the process power is concentrated at these discrete locations on the spectrum. Okay, process power has that kind of a concentration. Okay, so We will continue after 10 minutes.